energy and a new topic called work. Work is kind of I don't know, it has a specific definition in physics. So we're going to talk about what that definition is and how it's involved with energy and all that kind of stuff. But we're going to look at two main types of energy in this chapter. Do you know what they might be? Kinetic. Yep. And what's the other one? Potential. Good. Kinetic and potential. We've got two different meanings, and you see them in two different situations. But we're going to talk about now the conservation of energy. That's really the main point of this chapter. So we're going to look at energy and introduce kind of ourselves into the world of momentum. Momentum will be our next chapter, but both of these concepts are considered conserved. Do you know what that means? What's the law of conservation of energy say, and the law of conservation of mass? What do they say? Right. Mass cannot be created or destroyed, and it's the same thing for the law of conservation of energy. Energy cannot be created or destroyed. Goes with that? So, in order for there to have work done in physics, there's got to be a displacement that happens. So, what's displacement mean? The distance of travel. Right. That it's got to move. Right. If work is going to be done, the object has to move. Okay, so number one, we've got to have a displacement that takes place. Number two, there's got to be a force that's applied in the parallel direction of that displacement. Okay, so if you want to put in a little force parallel, you can. Okay, but we need to understand it's not really the same force parallel that we dealt with in inclines, right? That's not really what we're saying here. We're just saying that if we apply a force to an object, it has to move in that direction for work to be done. Okay, so let's look at an example here of this object applied at an angle. So in this particular case, it looks like they're pulling it upward, right? We're dragging our object. Okay, so our force is going at an angle right here, but my object is being displaced horizontally. Does that part make sense? We're dragging it. My object is moving horizontally. So in order to calculate work, we need to find the parallel component of that force. Okay, so we're not concerned about the force that's happening at an angle. The force that we would use to solve for work would only be the horizontal component of that force. Okay, because our displacement and our force have to be parallel to one another. Both have to be horizontal. Okay, so in this case, it says that the displacement is going to the right, and so we only use, technically in this part, the cosine of that force. Okay, we're only looking at the x component.
On our equation sheet, can we just do energy and work, or should we separate them?
They can be all in one chapter. Yep, they're going to go together. Okay, so your equation for work is force times displacement. And if you want to put that little parallel in, just to kind of remind yourself that that force has to be parallel, you can. Okay, so what happens if I push on this wall, push, I apply a big force to this wall? Am I doing work?
No.
No, why not?
Because you're not moving the wall.
I'm not moving the wall, right? There's no displacement that happens. I could be trying to lift something up. It's so heavy and I can't lift it. I might be feeling like I'm working really hard, right? But if that object doesn't move, then technically no work is done. Okay, so there is a difference in the physics definition of work and what we classify as working hard, right? Feeling like we're exerting work. There's a little bit of a difference. So let's try this one. If you pushed a loaded grocery cart a distance of 50 meters by exerting a horizontal force of 30 newtons on the cart, how much work would be done on the cart? Okay, my grocery cart, is it going to move in the horizontal direction or the vertical direction? It's going to move horizontal 50 meters. It says I'm applying a horizontal force of 30 newtons. So are those two parallel to one another? Yeah, so it's really a simple problem. All we're going to do is work equals force times displacement, right? That's newtons, that would be meters. And so, I don't know, that's what, 1,500? 30 times 50, okay. 1,500, okay. If we were going to just derive the units here, it would be Newton times meters, okay, but we've got a different kind of consolidated unit that we're going to use for work here in just a second, but it's just going to be joules, yep, so we're going to take okay. The units for the unit for work will end up being joules. 1 Newton meter is equal to 1 joule. Okay, so that one is true. Okay, we can work really hard or force. We can apply a force, but if it doesn't move, it doesn't work. What work is done on an object that's carried as you walk at constant velocity? So here's my object, and I'm walking. Is there work being done on the calculator?
No.
Why not?
Because The force is being put on it.
Okay, I'm applying a force.
It's moving with
It's
you.
a vertical.
Right, I'm applying a vertical force to hold it in the air, but it's moving what direction?
Horizontal.
Horizontally, right? So no good. But did I do work when I lifted it off the table?
Yeah.
Yes, right? There I'm doing work. If I'm sliding it, I'm doing work, right? Because my force is horizontal, my motion is horizontal. But if it's just being held and I'm walking horizontally, no good. Okay, no work being done. So I think the concept of work is a little tough to grasp because it seems counterintuitive, right? It feels like I'm working hard, but technically there's no work being done. So you just got to really make sure you're reading into the context clues and as to, is it being lifted, is it being carried, or whatever like that. You got to kind of be careful in how those things are
What
worded.
if you're, say, pulling something?
If I was pulling something, like if I had a rope
You could
attached
get
to
a
it,
wagon or something.
yeah, all right. So I'm still, that would count, right? Because my force, even though my force is at an angle, it still has a horizontal component. And so that would be the force I use there.
No, we're gonna get plenty of problems where it's like, if you're pulling something at a certain angle, you have
Right.
to figure out.
You have to find the x component of that, and then you could take it times your displacement. Yep. Okay, couple things we have to deal with when we're looking at work. The question will kind of specify, and you might need to specify, are you talking about the work being done by an object or the work done on an object? Okay. Most of the time, those values are the same, right? If I was pushing my calculator and I do 30 joules of work, that calculator is having 30 joules of work done on it, right? It's the same value. It's just kind of how that question is worded. So be careful when you're thinking about that. And then the last thing here is we have to specify whether the work that's being done is due to a single force or it's being done due to the net force. We're going to look at two different ways to solve that here. So we can find the work that's just done by gravity, right? By just using the gravitational force. We could find the work that's just being done by an applied force. Or we can find the net work of our system by taking our net force and looking at it that way. So we can do it two different ways. Okay? So that's what we're going to start with here. A 50 kilogram crate is being pulled along a horizontal floor by a constant force of 100 newtons exerted at 37 degrees. The floor exerts a frictional force of 50. Determine the work done on the crate. Okay, so this is just like the question Drew was asking about. We're going to look at how this box is moving and then determine what type of force do we need to be focused on. Okay, so it says it's being drug or pulled. So do we think the motion of our box is horizontal or is it vertical? It's horizontal. Okay, so it says it's going to move 40 meters. And so that means we really need to be concerned with horizontal forces. Okay, and we've got an applied force here and a frictional force. So we've really got two we've got to take care of. Okay, do you remember this part of our forces chapter? This is 100 newtons. This would be called F applied X. Do we need to bother solving for F applied Y? Nope, not in this case, okay? And then our angle here is 37. So go ahead and grab your calculator out. We're going to have to use a trig function here to help solve for that side of our triangle. It's adjacent, so what would we use?
Cosine.
Good. 100 times cosine of 37. Make sure your calculator's in degrees for that. I got F applied X equal to 79.9 newtons. Is that what you guys had? I don't know if you had to switch your calculators for calc or not.
I don't know, mine was in radians. I don't know why.
All right, then it says that our frictional force is 50 newtons. So that means if I want to find the net force of my system, what would I do? Right, positive minus negative, or force applied X minus the frictional force, right? That gives me a net force of 29.9. Okay, and is that net force horizontal or vertical? That's our horizontal net force. So if you want to put an X there, you can, just so you remember that it's the horizontal, but it's not really that big of a deal. So now if I want to find the work, I'm going to take the force parallel, which is 29.9, times my displacement, which is 40 meters. And I get 1,196 joules. The other way that you could do this is you could find the work done by F applied X. So take 79.9 times 40. That gives me 3196. You could take the frictional force times the displacement, which gives me 2000. So to find the work net, I would take 3196 minus 2000, and I still get 1196 joules. It's the same thing. So you could find the work done by each individual, but I just think that takes more time.
Why did you do that step in the corner of the F net?
Right here?
Yeah.
To find our net horizontal force, because that's what has to go in if we want to find the whole work of our system, right? If we want to find the total work done on the crate, right, that means we need the net horizontal force, or the net force that's parallel to our displacement, which was horizontal.
So if you didn't have friction, you wouldn't have to
That's
do
right,
that step.
right,
Okay.
right.
So if something was like, say, a hot air balloon, not just like anything being pulled.
This one's going to ask you to find the work done by individual forces. So kind of what I showed you on that last one. Determine the work a hiker must do on a 15-kilogram backpack to carry it up a hill at a height of 10 meters at constant velocity. So we just want the work done by the hiker. We don't want the net work, just the work done by the hiker. So he's got this backpack on his back. Oh, not a good color. Okay, he's got his backpack. He's applying that vertical force. That's it. Okay, so if I'm going to look at what that force is, what do you think I need to be? How can I determine that here? Right. Since this backpack, do you think the backpack is accelerating off of his back? No, the backpack is essentially at rest, right? He's moving it upward, but the backpack on his back is at rest, which means these two are equal. Agree? So if I want to find the force of the hiker, I'm going to make that equal to the gravitational force. Okay, so now that means I'm going to say that our mass times 9.8 is equal to the force of the hiker. So 15 times 9.8 gives me 147 newtons is the force of my hiker. But I want not just the force, I want the work. So this says the hill is a height of 10 meters. So do you think the 10 goes here or the 10 goes there? The hypotenuse or the...
Hypotenuse.
No, just the height, right? So this is telling us how tall the hill is. We don't care how he gets to the top of the hill, right? He could take the escalator for all we care, right? The same amount of work is done. So it's just about how high he's going to end up. It's not what's considered a path function. We don't care the path he takes to get there, right? Some things are path functions. This is not. We don't care how he gets there. It's just the fact that he's going 10 meters above where he started. So my work is 147 times 10, which gives me 1470. And what's our unit for work? Joules. Very good. Okay, and this is work done by the hiker. So is it positive or negative? It's positive because it's the one that's going upward. Okay? Now the next slide asks us to do basically the same thing. Find the work done by gravity. Right? We already found the gravitational force. We found Fg to also be 147. And doesn't gravity apply for all 10 meters of that hike? Yeah. So we're still taking work equals 147 times 10, which is 1470. So do you feel like this is an odd thing? Right? Why are they the same? The backpack itself is really not moving. Okay, so that means the net work on our system, oops, I didn't move forward there, okay. The net work on our system would be 1470 joules minus 1470 joules is 0, right? There's no work being done on that backpack because it's at rest on the guy's back. Right? I think work can be a little bit counterintuitive because it seems like we're doing a bunch of stuff, but really it's not the backpack that's moving, it's the guy, right? So that's a little bit different, but net work, we're always just going to take the net force times the displacement. Yeah.
If something slows you down, would it be negative?
Right. Mm-hmm.
I just asked.
Energy is kind of the stem of all science, right? We study energy and energy transfers in every topic of science, right? All of the sections of science we're going to look at it, but this is important. There's lots of different types of energy. We're going to talk about what's called translational kinetic and potential energy. And translational just means that we're talking about simple motion, like A to B. So not things that are spinning or rotating. We're just looking at things that move simply from A to B. Okay. The definition of energy is an object's ability to do work. Okay, and its ability to do work. So that means if we know what work is applying a force to displace an object. If I have energy, that means I have the ability to do that. I have the ability to apply a force that moves an object, right? If any object or system has energy, that means it has the capabilities of applying a force and moving an object. So that's what the definition of energy is, the ability to do work, okay? So we're going to look first at kinetic energy. What's the prefix kina mean? We use it in kinematics.
Motion.
Motion, right? So kinetic energy is the energy of motion. Okay? Anytime an object is in motion, it has kinetic energy. Okay? Anytime an object is in motion, it has kinetic energy. Okay? Kinetic energy is transferable. It's transferable. Okay? Which means one object collides with another object and sets that object in motion. That means it's been a transfer of kinetic energy. Can you give me an everyday example of when that happens? When do you see an object transfer energy to something else?
Like the
Mm-hmm.
Like the electricity.
Okay.
ball thingies?
Yep. Newton's cradle, right? Remember that? Any type of sport, any type of contact with a ball is a transfer of kinetic energy, right? If you swing your arm and hit a ball, if you swing a bat and hit a ball, that's a transfer of kinetic energy because that ball, let's think about a baseball. If a baseball's coming in, your bat swings, that baseball now changes directions, right? It completely changes direction. So the energy from your bat has now been applied to that ball to move it somewhere else, right? That bat did work on that ball, right? It applied a force, it displaced it. So kinetic energy is all over, and that transfer of kinetic energy is all over. What do you think would be considered a perfect transfer of kinetic energy? Like without losing anything with friction or without losing anything, how do you think a kinetic energy transfer could be perfect? What'd you say?
No gravity.
Okay. Yeah, that's a good example. Very good example. Okay, I want you to think about like playing pool. Okay, you take the cue ball, you hit another ball. Okay, what was that other ball doing first? It was at rest. Okay, so theoretically, a perfect transfer of energy means cue ball hits ball number 7 or whatever it is. This ball was at rest. The cue ball comes to a stop and exactly moves the way the cue ball was moving. That's a perfect kinetic energy transfer. So if this is moving 3 meters per second, this one's at rest. This one stops, this one moves 3 meters per second, right? That's a perfect transfer. But what happens more often in everyday life is this is moving 3, this is moving 0, now this is moving 2.8, and this one dribbles for a little bit until it comes to a stop, right? That's really what happens. But in a perfect world, a perfect kinetic energy transfer would be an absolute switch of energy, right? And that thing happens if objects are the same mass. They have to be the same mass for that to happen. And it's got to be perfect world, right? But anyway. Okay, that's transfer of energy. One object exerts a force on another and then work's been done. So here's your equation for kinetic energy. We're going to use this one all the time. Okay, so make sure you have this one. 1/2 mv squared. What do you think M stands for in here? This one? Mass. It has to be in kilograms. Mass is in kilograms. And what's V? Velocity in meters per second. Okay, so we've got to make sure our units are correct there. Bless you. Mass, velocity squared. The only thing that's squared in that equation is the velocity. It's not like the whole term is squared. Okay, just V is squared there. Okay?
What was velocity? What's velocity of the beam?
Meters per second. All right. Kinetic energy and any type of energy is also measured in joules. Okay, so everything we're dealing with in this chapter, work and energy, all measured in joules. Okay. All right, now we're going to start looking at how can we connect energy and work. Okay, this equation is called the work energy principle, okay, cleverly enough, okay, and all it does is connect that the work done on an object is the same as the change in kinetic energy of an object. So what does this symbol mean right here? Change in, and what does it also mean? What minus what? Final minus initial, okay? So the net work on any object is also equal to the change in kinetic energy. Okay, so I want you to think about this. If my object is slowing down, do you think my work is going to be positive or negative? It's going to be negative, right? If I'm slowing down, my final kinetic energy would be lower than my initial kinetic energy, which would result in a negative value there. Okay, if I'm speeding up, my network would be positive because my final kinetic energy would be greater than my initial kinetic energy. Okay, do you see how in your kinetic energy equation, 1/2 mv squared, right? It's really dependent on velocity because it's a squared velocity. So it's really, really dependent on that. So speed really has an effect on what its kinetic energy is. Okay, the network done on an object is equal to change. Oh yeah, okay, I just said that. Okay, the important part is on this one is that it only applies when we're talking about net work. So we couldn't plug in the work done by gravity and make it work here. It has to be the total, right, the net work. Let's try one here. 145 gram baseball is thrown with a speed of 25 meters per second. What's its kinetic energy? How much work was done if it started from rest? All right, so first things first, do we see any red flags here?
It's in grams.
It's in grams, right? That has to be converted from grams to kilograms, okay? Okay, so if I want to go from grams to kilograms, I'm going to go 145 grams divided by 1,000, right? Really, you can just move the decimal if you want, but that gives me 0.145 kilograms. Okay, I want to know its kinetic energy at the time it's moving 25 meters per second. So I'm going to say KE equals 1/2 times M times V squared. Okay, 1/2 times M times V squared. I got 45.3 joules. Okay, and so if it's starting from rest, what does that mean its initial kinetic energy is? It's 0. Okay, so if I want to find the work done, I take final kinetic energy, 45.3 minus 0, and that means my work is equal to 45.3 joules also. Right? If it had given us an initial velocity, let's say, what's the work done from 10 meters per second to 25, then I would have to do that calculation. But when we start from rest, that means our initial kinetic energy is 0. Okay, so we're just looking at start to finish there. Okay, questions about that? Simple enough? Okay, very good. All right, let's try this next one on your own. How much work is required to accelerate a car from 20 meters per second to 30 meters per second? Okay. We're going to look at that equation there. Work equals change in kinetic energy.
So do we do both the equations and then subtract?
That's what I would do. You could technically, I don't know what it's called, factor out the 1/2 and the M and work it from there, but I just leave it. Did we make sure to go 30 minus 20? Right? Sometimes we just read it in the problem and plug it in, but 30s are final, 20s are initial.